In the last section of Chapter 14, Equilibrium, we're going to be discussing Le Chatelier's principle. And the question would be, what happens when equilibrium is disturbed? For example, if we consider hemoglobin, in the case when someone is anemic, that is, they have a low concentration of red blood cells, how does the body respond in order to supply oxygen to all of its needs? So we'll be answering those questions and looking at some example problems. Starting with some definitions. First is Le Chatelier's principle, and this tells us that equilibrium will shift either to the reactant or the product side to minimize the disturbance. So, for example, if one of the reactants is removed, the equilibrium will shift to the reactant side to replace the reactant. The second term here is Q, and Q is defined as the reaction quotient. In formula, it's the same as KEQ, where we have the products of the reaction to some power, depending on the mole ratio, over reactants to some ratio. But Q is not necessarily not at equilibrium, or at least it tells us what the state of the reaction is. So if we solve this and Q is larger than KEQ, then the reaction will shift to the left. If Q is less than KEQ, the reaction will shift in the other direction. So what does that mean in terms of the practical, which do we have more of, products or reactants? In the case where Q is greater than KEQ, it means that there are more products. And so the reaction is going to shift to make more of the reactants. Likewise, if Q is less than KEQ, that means that there are more reactants as compared to KEQ, so the reaction would shift to the right. Since we're talking about reactions largely in the gas phase, remember we can have gas, atmospheres or concentration, as well as aqueous solution concentration. Solids and liquids are not included in K or Q. Because we're thinking about things in terms of gas phase largely, some of the variables that are going to impact what happens when the equilibrium is disturbed are 1. Pressure or volume, 2. Temperature, and 3. Amount. Okay, so this goes directly back to the ideal gas law. PV is equal to nRT. We have pressure volume, we have temperature, and we have amount. Remember that R stands for the gas constant. All right, here is an example reaction where we have 2NO4 dinitrogen tetroxide going to 2 nitrogen dioxide. If we were writing an expression for KEQ or Q, if we're not sure if it's at equilibrium or not, it would be the concentration of nitrogen dioxide squared, because they're 2 moles, over the concentration of dinitrogen tetroxide. Right, looking at this reaction, we're told that in this case, more nitrogen dioxide has been added. So we've increased the amount of NO2. So what's going to happen here is that the reaction is going to shift back to produce more of the reactant. So shifts to reactant. And this is done to reestablish equilibrium. Whoops, let me erase that there. Reestablish equilibrium. Here's a graphical representation of what we just discussed in the previous slide. In this case, we added more nitrogen dioxide to the reaction mixture. So it is possible for there to be a collision between those two reactants. The equilibrium is disturbed, and the equilibrium shifts back to producing the reactant, dinitrogen tetroxide. We can also look at this in terms of what's happening during the reaction. Okay, here at the start of the simulation, the system is at equilibrium. So in that case, Q is equal to K. But we disturbed the equilibrium by adding some of the product, nitrogen dioxide. So now Q is not K because we've increased the amount of NO2. So let's just say, for instance, we had KEQ equal to 3 over 2 or 1.5. Okay. And then when we disturbed it by adding more of the product, let's say we went to 5 over 2. So now the ratio is 2.5. Right, equilibrium tells us that this value is going to be constant at the same temperature. So in this case, Q is greater than KEQ. So the equilibrium will shift back to making more of the reactant. And so now we would end up with some ratio again that is going to equal 1.5. So after equilibrium is established, Q and KEQ would be the same numerical value. Here's the opposite circumstance. In this case, we have the same reaction. Remember, we're going from N2O4 to 2 nitrogen dioxide. All right, so in this case, again, starting, Q and K are equal. This time, we've disturbed by adding more dinitrogen tetroxide. Okay, so in this case, this is going up, which would shift equilibrium to the products. Okay, we can see that shown up here, that after that point, the amount of nitrogen dioxide increases and equilibrium is reestablished. Now we want to consider what the effect of pressure is, and we really have to consider pressure and volume together. Remember that Boyle's law tells us as volume decreases, pressure increases. Vice versa, as volume increases, pressure decreases. So, related to the pressure and volume of gases, Le Chatelier's principle also includes that as pressure goes up or volume goes down, equilibrium will shift. Let me erase that. Will shift to the side with fewer moles of gas. All right, so that's the relationship between those. Let's look at this example. We have nitrogen plus hydrogen gives us ammonia. Notice that there's 1 mole of nitrogen and 3 moles of hydrogen on the reactant side. That's a total of 4 moles of gas. And there are 2 moles of ammonia on the product side. Right, so in this case, volume decreased. Remember, we represent that by pushing down on this movable piston. So pressure is going to increase. The amount of collisions would go up. There's less space, and those molecules would collide with the sides of the container more frequently. That would be an increase in pressure. And so in this case, because we have a reactant with 4 moles and a product with 2 moles, equilibrium would shift to the right, to the product side, because there are fewer moles of gas. Right here is the other circumstance looking at this same reaction. Again, we've got this movable piston, okay, and so this time we're increasing volume. Volume's going up, and so pressure is decreasing. They are inversely proportionate. Right, so same thing, 4 moles of gas on the reactant side and 2 moles of gas on the product side. So because pressure is going down, because pressure decreases, equilibrium will shift to the side with more moles, or in this case, the reactants. So far we've talked about the effective amount, N, if we add or remove a reactant or product. We've talked about pressure volume effects and how the equilibrium will be changed. Now we want to look at temperature. Let's remind ourselves, for an exothermic reaction, heat is a product. And for an endothermic reaction, heat is a reactant. So just like we're thinking in terms of amounts, in this case, heat is on the reactant side, so it is an endothermic reaction. I can also tell that from my sign of delta H, remember? If delta H is positive, it's endothermic. If delta H is negative, it's exothermic. Right, so I can represent it in one of 2 ways, either from looking at the sign of delta H, or whether or not heat is on the reactant or product side. Okay, so in this circumstance, heat is a reactant, which means it is an endothermic reaction, and let's say that heat is added. So this would be just like any other reactant, causing a shift to products. So how do we add heat? We just warm up the test tube. How do we remove heat? We put it in an ice bath. As I just referred to on the previous slide, this is an endothermic reaction. And we see that heat is a reactant. So in this case, my test tube is in an ice bath. Okay, I know that the reactant is clear or colorless, and the product is this brown gas, nitrogen dioxide. Okay, so when we put it in ice, it shows me that it is clear, which means that the reaction has shifted to the reactant side, because we have removed heat, or one of the reactants. Right, in the second picture here, we're shown that the temperature has gone up, and we see that we've got a warm bath for this container. And now that we have added heat, the reactant shifts to products. And we can see the change in color from clear to brown. Let's look at an example problem. We have an equilibrium problem. NH4 solid is in equilibrium with two gas products, NH3 gas plus H2S gas. If I were writing KEQ, we would have the concentration or pressure of ammonia times the concentration or pressure of hydrogen sulfide over, now notice that this is a solid, okay, so that means that it does not go into my equilibrium formula. So I could just put 1 there, or another way to write that is just simply to put NH3 times hydrogen sulfide. Okay, let's say that we know that Kc for this reaction is 8.5 times 10 to the negative third. And I'm told that I have 0.166 molar of ammonia and the same concentration of hydrogen sulfide, 0.166 molar. So is this reaction at equilibrium? All right, so what we need to do is solve for Q. Because we don't know if it's at equilibrium, we call it Q. But we're going to solve it the same way as we have this formula up here. Their concentration is the same, so I'm just going to square this number, 0.166 times 0.166, and I'm getting 0.0276. Right, now I want to compare back to my Kc value. Let's see if I can move this up, okay? And I'm told, I know that Q is 0.0276 and K is 0.0085. If I go ahead and write that in expanded notation. Okay, looking at these two numbers, I see that Q is greater than KEQ. So that tells me that I have more products than when the system is equilibrium, and so it is going to shift back to the left. Or in other words, more solid. Oh, this was ammonia. I'm sorry, I did not write the full compound name up here. It's NH4HS. So we get more solid NH4HS. In my second example problem, we're looking at this equilibrium. Carbon monoxide gas plus chlorine gas goes to COCl2 gas. Right, so we have three circumstances here. How does equilibrium change? Generally, we're not looking at Q this time. So we add COCl2 is added. Right, so we're adding to the product side. That would be more P, so the equilibrium is going to shift to make more reactants. Number 2, chlorine gas is added. Right, so in this case, I've added more reactant, so it will shift to make more product. And the third example, if COCl2 is removed. So in this case, the equilibrium will shift a product to make more of that particular product. Right, we've looked at two different examples. One is more of a quantitative look at Le Chatelier's principle, and then the second is more of a qualitative look. In class, I will be doing some demonstrations to illustrate this principle, as well as giving you another problem set to answer some questions and test your understanding.